Welcome back to part 7 of my simple constant current load. We are exactly where we left off in part 6, card link. Only difference, everything is shut off for the moment. So in this part I want to implement the power limitation for that thing, slash current limitation. And you know, there was some hiccup about the performance of the heatsink here that threw me a little off, but I'm over that, and yeah, we shall proceed. But first I want to go a little bit into theory and details why I was so off regarding the performance of the heatsink, and afterwards we talk about a little bit how to limit with a single op amp the power dissipation. Yeah, it's an approximation, but it uses only one op amp. Yeah, let's get started. So in part 5 I measured the performance of my heatsink in combination with the thermal pad below my TO220 case. And yeah, adding in the internal thermal resistance from the chip to the case, I came to a maximum power dissipation of 21.7 watts. Yeah, card link. And basically the combination of heatsink and thermal pad, I measured 5.21 Kelvin per watts, and 10% for measurement errors, 5.73 Kelvin per watts. I repeated that measurement and came to similar values, a few hundreds Kelvin per watts off, and then I stopped right there. So my theoretical reasoning went like that. Okay, I have that heatsink here. Yeah, that was its original look, and you remember we cut off these outer ribs here. Yeah, card link to the part. And these are 12 ribs, but these are big ribs, okay? So I said, the performance of the heatsink will degrade by a factor of 12/8. Or I have to multiply the 1.8 Kelvin per watt given for that thing by the manufacturer by 1.5. Coming to, you can't read that anymore, 2.7 kelvins per watt. And then we also took down the depth of the whole thing. We reduced it from 50 millimeters to 36 millimeters. That gave me another factor of 1.39. And multiply the 2.7 Kelvin per watts by the 1.39, you arrive at these 3.75 kelvins per watt here. And at the thermal pad with either 0.3 or 0.5 Kelvin per watts, you arrive at a pessimistic approximation of 4.3 Kelvin per watts, or if you are very optimistic, 4.05 Kelvin per watts, which is a far way from the 5.73 or 5.21 I actually measured. So where did I go wrong? First, I could have had a look into the data sheet of the heatsink, because the manufacturer included there a curve where you have the thermal resistance in relation to the depth of the heatsink profile, because they sell it not only in 50 millimeters, which I bought, but also in 75, 100, 150 and 200. And yeah, I cut down from 50 millimeters to, what was it, 36. And you see the thermal resistance in that region, if you shorten the depth, it's not increasing in a linear fashion, more in an exponential fashion. So yeah, that was my first mistake. Yeah, I just assumed that the thermal performance would just deteriorate in a linear fashion, but it does not. It's more like, I don't know if it's really exponential, but it looks pretty exponential to me. Yeah. And the reason that curve being an exponential curve or something like that is how these passive heat sinks work. They rely mostly on convection. Yeah, there's also some heat radiated away in form of infrared, but yeah, the bulk of the heat is transported away by convecting air. And that means cold air goes in here, is heated up, and therefore it rises, yeah, like hot air balloon or better chimney, until it comes out again and it sucks fresh cold air from the bottom. So yeah, it's convecting, yeah, that's the name. And yeah, it basically works like a chimney. And what happens if your chimney gets shorter and shorter and shorter? Well, it draws less and less smoke, because yeah, chimney needs a certain length to work. Yeah, that was number one. Number two, the manufacturers give their performance data for standard conditions, and that means usually 20 degrees Celsius and 1 atmosphere or bar, so at sea level. Hey, so but I'm not at sea level here. I'm at about 300 meters, roughly 1,000 feet. So the air pressure here is already down about 3%. And yeah, this has an influence on your convection cooling, because the air is less dense, and less dense air can transport less heat. If you don't believe me, think about the extreme. In vacuum, there is absolute no convection cooling, yeah? And now you tell me why. Certainly, when in vacuum, there's absolutely no convection cooling at, for example, 0.1 atmosphere or bar, there is suddenly the same convection cooling like at sea level at 1 bar. It doesn't work that way. You lower the pressure, your convection cooling gets worse. Same is true for the ambient temperature of the air. At 20 degrees Celsius, the air does better convection cooling than, let's say, at the, what was it? Yeah, 30 degrees Celsius, I was measuring the performance. So yeah, you could make an hour-long video about all these factors and yeah, what their influence is. It's linear, exponential, or whatever. But yeah, I was too simplistic in calculating my heatsink. And now let's continue with power current limitation. Huh? And for that, let's first have a look at that red curve here. So in this graph, this is the current flowing through my load from 0 to 3 amps. And this is the voltage drop across my load from 0 to 40 volts. And I can at most burn 21.7 watts. So depending on the voltage, that I drop, I can let that current I equals 21.7 watts over the voltage flow through the load without burning it up. I equals P over V. And for the mathematically inclined amongst you, this curve is a hyperbola. And you cannot calculate a hyperbola with a single op-amp. So we need some approximations here. And the first thing you noticed is that here is kind of a cutoff, a plateau, and here. So what's that about? So my upper current limit is obviously given by the current regulation. What's the maximum current I dimensioned it for, and that was 2.5 amps. If I haven't done it, card link to that part. And the lower plateau is given by the fact that I can draw this point here with my power limitation down to 0 volts after that diode here, which supplies me with a voltage drop of 0.6 volts. So I can at minimum limit the current by pulling that point to 0.6 volts, and that leaves me with a lower limit of 0.639 amps. I cannot decrease the current any further. I cannot go lower than ground down here, and 0.6 volts voltage drop. And I've updated it, and I also changed these two resistors in the schematics. I needed to be able to draw the current even further down than I have anticipated for set reasons with the heatsink. And so between my upper limit of 2.5 amps and my lower limit of 0.639 amps, I will do a linear approximation of my hyperbola. And I can do that linear approximation with one op-amp. Has some drawbacks. I mean, we obviously lose some parts of the safe operating area. But these are only small parts. And you also noticed I'm cutting in here into the death zone a little, which is okay, because remember, the 21.7 watts are also dissipated partly by our shunt resistor, not exclusively by the MOSFET. And every line or linear function can be described by just 2 points. And when I was fiddling around here optimizing, I choose these 2 points. So the first point here is at 4.32 volts. I want 2.5 amps, my maximum. Initially with the better heatsink, that voltage was much higher, 5 or 6 volts. But hey, I can still put 2.5 amps at a fully loaded lithium-ion battery. So, okay. And the lower point here I choose, at 0.75 amps. That's a little easier to, in my head to work with than 0.639 amps for 23.3 volts. So, Yeah, so at 20 volts we still have, we can draw 1 amp. At 10 volts we can almost draw 2 amps. Yeah, it's a linear approximation, and I think it's still very useful. Not as powerful as I imagined, but useful. And in turn, in the circuit, these currents translate to specific voltages at the output of my power limitation. So for 2.5 amps, that's easy, 1.75 volts. And for the 0.75 amps, I need 0.105 volts. How do I get to these voltages? And the answer is simple. I mean, at that point, a certain voltage corresponds to a certain current in my current regulation, and then I have to subtract the voltage drop of 0.6 volts. So for example, for my full 2.5 amps, I need a voltage here of 2.650 volts. Yeah, subtract the 0.6 volts voltage drop here. So if my point here, be in the power limitation, my op-amp output beyond the diode here is at 1.75 volts, I can go up here to the full 2.350 volts. And in between the 750 milliamps, I won't try to calculate that in my head now. Okay, so let's have a look at that circuit down here where you just saw the diode up until now. And there is one critical aspect about that diode here, the 1N3595. Its reverse current is below 1 nanoamp. Remember, this is limiting. So if here at this point here, I marked it V out, the voltage is lower than plus 0.6 volts up in my current limitation, then I want to draw that point up there down to this voltage. If it's higher here, nothing should happen. So that will, that diode is preventing that current limitation circuit to actually increase the current that is flowing. And since my voltage dividers up there are quite high impedance, it's important for that diode to have a very low reverse current. The rest of the circuit consists of an op-amp in basically inverting amplifier configuration. So you remember our current limit, the curve goes downward, and combination with a single adder here of a positive voltage. So we actually shifting that curve that would normally go through 0 a little bit. And so we implementing exactly, the voltage curve or linear function we need here. If you want to know the details about how to calculate that from the 2 points, I've got a video up for that, card link. I won't go into the details here because, I want to keep it under 1 hour. Something else notable here. I have 10K resistor here to ground. That basically has a normal operation, no function at all. However, if you switch the load off and you still have an input voltage here, you have kind of a voltage divider going here down to ground that will, for 60 volt input voltage, limit the whole thing to, at that point, a maximum of 4.8 volts and, yeah, you see 15 meg here, current of maximum of 4 microamps. And I'm hoping, I do not know, I'm hoping that the op-amp will survive that. Okay, so we'll have at least for 25 volts or so some destructive testing, maybe destructive testing ahead of us. So let's wire the thing up and test it. First, a little close-up of the breadboard. Yeah, these are all the resistors, and the little black blob here is the diode. Yeah, if you count it, there's one resistor too many there. That's because I don't have a 15 meg ohm, yeah, on hand, so I have two 7.5 meg ohms in series. And yeah, that light yellow cable here that goes over to the diode buggers off to my current regulation voltage divider. Yeah, let's power it up. So for that we don't really need the oscilloscope. This is the input voltage and this is the output voltage of the op-amp right here. So if I turn up now the output voltage is now at 2.1 volts. So plus a diode drop, it should have any influence on the current regulation. And if I go up to, what was it, 4.3 volts, let's see, it's falling. Yeah. .3 to 1.74 volts, which was exactly, yeah, at 4.3 volts, 2.5 amps, and that means I need 1.75 volts at that output of the op-amp. So that's up to that voltage we can draw the full 2.5 amps. And yeah, sorry, I will probably it should actually, sorry, be okay. Let's go up to 23 volts. And I need to change the range here on the cheap meter. 23 volts. Yeah, almost, and we are down to 0.21. And yeah, at 23.3 we should be finally at 0.105. Yeah, dragging the current down really to 750 milliamps. So that, at least the, the output of the op-amp works fine. In turn, I shouldn't be able, yeah, the green numbers here, to turn up the current much over 800 milliamps now, should I? Let's try that. So 500, 600, and that's it. It's limiting, but it's limiting at 600 milliamps, which is a wee bit less than I expected. I mean, I hope you can read it. It's stuck at 650. Should be at least 750, so yeah, something is not okay. But if I decrease now the voltage, my current should go up. Yeah, and you can see it. Wonderful. So in principle it works, but okay, and now I overloaded my lab power supply. Sorry. to turn down the voltage again. It went into overload. My power supply went into overload. So we were nicely moving up and down that curve. Only it seems to be that that curve is a wee bit too steep. And yeah. Let's see what that's all about. So I built up the whole circuit mostly with 5% resistors instead of the 1% I want to use. So there is, of course, 5%, a little variation there. It's in the order of magnitude. But another assumption I made was the voltage drop across the diode being 0.6 volts. And yeah, that's the value you use for its voltage drop for a diode. And yeah, maybe we should measure that. And the voltage drop across the diode is indeed only 531 millivolts. So yeah, we are a little bit too low there. And I have the pot at the full counterclock position. So the maximum voltage on our current regulation circuit. Yeah, so it might go up to 600 millivolts under extreme conditions. So really input voltage 35 volts. And yeah, I mean, it's a diode. The voltage drop changes according to the current that it's going through. That's a drawback of that very simple circuit. But I almost think I will leave it at that for the moment and maybe fine-tune it later. For now, we have completely finished building up the circuit. And now the destructive test. So I have over 20 volts at my input and I switch it off. Yeah, current goes to 0. Yeah, we tested that, everything. Now I switch it on again. And I should again produce a voltage drop, which is now, oh yeah, I turned the pot. So I turning the pot here a little bit. Yeah, we come back up to 500 something and we are having 700 milliamps flowing. And if I now decrease the voltage, the current still goes up. So yeah, op amp has survived. Very nice. And yeah, dash count limitation of my power supply, which is obviously not a match for the constant current load I built. So yeah, wonderful. So next time, well, I have of course to make a layout, single-sided layout for that whole rat's nest here. But next time I want to do some transient analysis testing. So how does a thing behaves when suddenly the load or the input changes? How does it behave when you suddenly switch it on or switch it off? Yeah, we already tested causally, yeah, little how it behaves when you switch it off. But yeah, all these extremes just to see if, yeah, nothing explodes and yeah, nothing is swinging. Well, until then, bye.